Alright kiddies, today we're going to do an experiment where we determine the identity of an unknown cation via a titration in a reaction that you're actually familiar with. Let's go ahead and get started. So I have here an ionic compound, and I know that it's a monochloride, meaning that there's one cation attached to a single chloride ion. Thus the cation has to have a +1 charge. What I got to do is figure out which cation is this. So let's take a look at some options. Well, we know that the +1 ions are going to be in this region right here on the periodic table. Those are our +1 guys. Oh, sure, we know that silver can be +1, gold also can be +1. And there's other ions in here that can also be +1. We're not going to worry about that. It's going to be one of these, or possibly our little friend, the ammonium ion. That's also a +1 ion. So the cation that's attached to this has to be one of those guys. A lithium, a sodium, potassium, rubidium, cesium, or ammonium. Let's take a look. So the purpose of the lab is to determine the identity of the unknown cation via this technique we're calling a titration. There's something bonded to the chloride here. What is that thing? Here's what we're going to do. We're going to record the data regarding the preparation of the unknown monochloride solution below as directed by the teacher. Hey, that's me. What we're going to do is we're going to dissolve this, a certain amount of it, into some water so that we can actually titrate it. Again, we need this to be aqueous so the ions can move back and forth. So we're going to measure the amount that goes into the solution and then record the volume of the solution created so we know something about its concentration. Let's go ahead and do that. We have 0.575 grams of the substance. All right, I've taken that 0.575 grams of our unknown chloride and dissolved it in water until I created 50 milliliters of solution. By the way, I did not do that in this Erlenmeyer flask. I did that in a graduated cylinder. You don't measure volumes quantitatively with beakers or flasks. Where's my beakers? These are not designed to read volume. They're just holders. We want things that are graduated more precisely, like graduated cylinders. So my 0.575 grams of my unknown chloride were dissolved in enough water to create 50 milliliters of solution. Ooh, that's important. Let's move on. Okay, so I'm going to react those chloride ions with our old pal silver ion. And we know that silvers will react with chlorides to form silver nitrates at a 1-to-1 ratio. So we know our silver ions are going to react with the chloride ions to form a solid silver chloride. So by adding silvers, we're essentially removing the chlorides from the solution. So what we're going to do is go ahead and load our burette. Now this guy is the burette, this tall, skinny tube. And you'll notice at the very, very top, it's graduated with a 0 where my thumb is. Kind of hard to see on the camera. But then it graduates down 1, 2, 3, 4, etc. all the way down to 50 at the bottom. And there's a little valve stem at the bottom which allows me to control how much of the solution I am going to release. That's going to go down into our solution of the monochloride. So I'm going to introduce those silver ions from the burette into this monochloride. And I'll know the whole time how much I've added through the burette. So what I'm going to do now is actually fill the burette with a 0.100 molar silver nitrate solution. So I've closed the valve on the bottom, the little stopcock that stops it from coming out. And I'm going to fill it up carefully. Remember, silver nitrate is very photoreactive. If I get it on my hands and the sunlight hits it, my gosh, my hands are going to turn black, like a henna tattoo. But I really don't want that. So what I'm going to do is fill it up past the 0 mark here. And then my funnel out carefully. And I'm going to release the valve until I end up with the line the meniscus, right at the 0 mark. Coming down, coming down, coming down, stop. Ah, perfect. So now I'm starting with the amount of silver nitrate with the bottom of the meniscus sitting at 0. I'm going to know exactly how much I put in because you can see it's graduated down to 1, 2, 3, 4, 5, 6, etc. All right, the next step is I'm going to obtain a certain amount of my monochloride in a measured device, my graduated cylinder, so I know exactly how much I'm analyzing. So I started with 50 milliliters, but I'm only going to analyze this amount. This measurement is important. So now what I'm looking at is past 22. I'm going to go with 22.4, maybe. The last one is obviously the estimate. This past 22, not 23, 22.4 seems like the right measurement. So I'm only analyzing 22.4 milliliters of the solution. Originally it was 50 milliliters. So there's only a certain part of this that's going into the analysis. All right, my next step is to add the 22.4 milliliters of our unknown chloride to an Erlenmeyer flask. Then I'm going to rinse that flask. I've got to get all the chlorides out of there that I can because I need to account for every one of those buggers into the flask. Now I'm going to add an indicator solution. My indicator in this particular case is potassium chromate. Nice yellow substance. And I'm going to explain to you how the potassium chromate works as an indicator. All right, so my brilliant artistic work here shows a burette and this Erlenmeyer flask that has been melted in a horrible accident. But my point is, we have silver ions in our burette. We're going to be adding those to the chloride ions in the solution. I've added potassium chromate. Chromate, as you saw, is a yellow ion when it's by itself. And the idea here is that as I add silver ions, the silver ions are going to preferentially bond to the chlorides. They would rather be with the chlorides than they would the chromates. So when I add silver ions, they look around the room, they say, ooh, I like this chloride over here. And they bond to that chloride to form a solid. It kind of reminds me of when I was your age at high school dances. I was a lot like the chromate ion. So my friends were chloride ions. I was the chromate ion. We'd go to the dance, and the girls, who were the silver ions, would start showing up. And they'd walk in, they'd look around the room, and they'd say, oh, can I dance with you? And one of my friends would go off and dance away. And then the next girl that came in, the next silver ion, look around the room and say, oh, I want to dance with that chloride ion. And one of my friends would disappear. The next one would come in and pick the last friend. And pretty soon, that poor girl that came in towards the end looked around the room, and there was no one left except for me. When that poor girl had to bond with the chromate ion that was me, that compound, silver chromate, is actually red. So what does it tell us when this whole solution starts to turn red? It says all the chlorides are gone. Now the silvers are bonding to the chromates. That is our end point of the reaction. All right, so here we go. I'm going to start allowing the 0.1 molar silver nitrate into our unknown chloride solution. Of course, it's getting cloudy. I'm swirling to make sure everything reacts. Still staying yellow. So none of the silvers are bonding to the chromates yet. Oh, there we go. There we go. And boom! Perfect. Now we got to check the volume. And you'll notice it's graduated upside down. So our meniscus, which is right there, is between 34 and 35. It looks to me like 34.4. All right, so we took 0.575 grams of our unknown chloride and dissolved it in 50 milliliters of solution. Then we obtained 22.4 milliliters of that solution. So do we know how many grams were in there? Well, we can figure it out. Now the other part that's important, we know that we used 34.4 milliliters of a 0.1 molar silver nitrate solution. So we know how many moles of silver went in there. If we know how many moles of silver, we know how many moles of chloride. This is our moles of silver. That's what we've been drilling on. Once you find moles of silver, you know how many moles of chloride. And from there, it's all gravy, because you just have to figure out what else is attached to that chloride that would amount to the masses that we obtained in the beginning. Ah, so fun. All right, I'll see you in a bit. Good luck.